Now, I know what some of you guys might be thinking. I didn't answer the question. It says, find a Lagrange error bound for the maximum error when the absolute value of x is less than or equal to 1. Not when x is equal to 1, but when x is less than or equal to 1. In other words, x doesn't have to equal 1. X could be anything between -1 and +1. Well, I contend that I still answered that question because if I try to maximize the fifth derivative of the function between -1 and +1, then I'm still going to get 3, right? Because the biggest e to the x is ever going to be on a closed interval is the largest x value possible. Again, this is an increasing function. E to the x is increasing. So we can safely say that not only is this the maximum error when x equals 1, but we can say this is the maximum error when x equals anything between -1 and +1. And to illustrate that, we've got a graph over here. So we've got 3 different functions graphed, and I encourage you to try to figure out what each function is before I label them. So let's see, the blue one. The blue one, well, that has that horizontal asymptote on the left side, right? That's got to be the, let's see, y equals 0. That's got to be the exponential function. So f of x, right? F of x equals e to the x. Now, if you look at the red one, let's see, I need a red color here. If you look at the red one, you can see that it follows e to the x pretty nicely, but over here on the left side, it does not approach a horizontal asymptote. It seems to curve back up and starts increasing, which exponential functions don't do that, right? They don't have a minimum. They are monotonically increasing or decreasing. So this one must be a polynomial approximation of e to the x. So I'm going to call that, what did I call it over here? I called it p sub 4, right? This is p sub 4 of x. And that one is the fourth degree Taylor polynomial centered at x equals 0. So that was 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial. Now, we evaluated, we evaluated p of 1, right? So when we went up to here, we ended up at that point right there. That point was the point 1 comma 2.708, I believe it was, or so. And we noticed that was very stankin' close to e. In other words, when we evaluated this function f of x at x equals 1, we got 1 comma e, right? So that blue dot and that red dot are very, very close to each other. So what's that purple function? Does anyone know? I think that some of you might. It kind of gets bigger as x gets farther away from 0 over here, and it kind of gets bigger as x gets farther away from 0 over here. But when x equals 0 and when x is near 0, that purple function is almost not even noticeable, right? It's very flat, very close to 0. This purple function, guys, that's your error. That's the r sub 4 of x. Okay? How did I graph that if I don't know what r is? Well, I simply just typed into Desmos. I typed in the absolute value of p sub 4 of x minus f of x. Okay? So there's no approximation here, or I guess there's no significant approximation here. This is the actual function that represents the difference between the Taylor polynomial approximation and the actual transcendental function. And what we're saying over here with this 0.025 is that 0.025 is bigger than all of the y values of r sub 4. And that's not everywhere, but that's in this interval right here. So between -1 and +1, the y values of this function, this purple function, are so small, they're in fact smaller than 0.025, guaranteed. And you can play around with this and you can see that is in fact true if you type that into a calculator. Of course, that's not true for all values of x, because the farther away from this point right here, 0, 1, that point over which the Taylor polynomial hugs the exponential function, the farther away we get from that point, the worse the approximation is going to get. So by the time we get out to x equals 2, for example, the error is noticeably bigger. it might be around 0.5 or so. I'm not really sure, but something definitely bigger than 0.025. So, and likewise, going in the opposite direction, if we go farther away from the center over here, we get to -2. Perhaps the error is not quite as big over there, but it is definitely noticeably bigger over there as well. So this approximation is within 0.025, as long as we stay within a certain local area for this function.